Well, so now I turn to my subject. So my subject now, I did some of this last time. This is about mostly geometry of roots. So you remember what we have. I can repeat whatever I wish. We have a semi-simple, but better simple, Lie algebra, G. Cartan subalgebra, H. Dimension of this Cartan subalgebra, we can denote it as R, mostly because it is called the rank of the Lie algebra. This Cartan, this space H, is the home of very special elements H alpha, but alpha are roots. Alpha belong to H star. So there are roots. And G as a vector space is the sum of G0, which is H actually. And as such, it is the same. So G0 is the same as H, the definition of Cartan algebra, and also one-dimensional spaces G alpha, root spaces. So the dimension of G becomes the dimension of HR plus the number of non-zero roots. Also, there is the Killing form, symmetric bilinear form on this space H or H star. It is the same since it is non-degenerate. And then there are different relations between inner products of roots. So first of all, I repeat this and hope that you remember this. If not, I can repeat it. That something wrong? No. For any two roots, alpha and beta, alpha should be not zero, beta is arbitrary. The number 2 alpha beta divided by alpha alpha is an integer. Moreover, this integer actually has the following meaning. There is an action of SL2 in the space, the sum, so this space becomes G beta plus K alpha. K here is from P to Q, and this beta plus K alpha, beta plus Q alpha, and so on, beta plus P alpha, so P is less than or equal to 0, Q is non-negative, P is non-positive, and these are roots. They form a series of roots. If 0 is among these roots, then we need to replace G0 by CH alpha. So this is what we have, and these numbers are inner product alpha beta divided by alpha alpha are actually eigenvalues of H in this space. So they are integers. They form a symmetric sequence of integers with such an arithmetic sequence with the step 2. So is it okay? Do you need to repeat anything? Yes. Then, from this immediately, I can deduce that if alpha is a root, non-zero root, and lambda alpha for some complex number lambda is also a root, then lambda is 0 plus minus 1. We know this already in the case when alpha is an integer, well, when lambda is an integer. 2 alpha is not, if alpha is a zero root, 2 alpha is not a root, we know this. Now, we can extend this to the case when we can consider root lambda alpha with any lambda, complex number alpha. Now look, if alpha is non-zero root, and lambda alpha is also a root, then 2 lambda alpha alpha divided by alpha alpha, and this is not 0, we know this, which is 2 lambda, is an integer. So for lambda is not, I say complex number, but actually lambda is either an integer or half integer. If lambda is an integer, then we already know that lambda is plus minus 1 or 0. What if lambda is a half integer? So 2 lambda is odd. Then look, we have again a root series, lambda alpha plus k alpha. This is beta. And now lambda plus k divided lambda plus k, lambda plus 2k, excuse me, become eigenvalues of h, right? And they form a symmetric sequence of integers, symmetric with vector 0. And since it's symmetric, then we see that for some k, lambda plus 2k must be equal to 1 for some k. No, 2 lambda plus 2k, right? Which means that 1/2 alpha is a root, right? That lambda is 1/2. This is a root, which is certainly impossible because alpha is a root. And this is a contradiction. Because alpha is 2 times 1/2 alpha, cannot be a root if 1/2 alpha is a root. So we see that actually if alpha is a root, then no vector, alpha is non-zero root, then no vector proportional to alpha, with the exception of 0 and plus minus alpha, can be a root. It is interesting. Now next thing, we consider a complex vector space. I mean H or H star, whatever, with an inner product. So at this moment we cannot speak of it being positive or whatever. But still, something happens. Look. I consider some pair of roots, beta and alpha. I consider this representation of SL2, and the two extreme eigenvalues of H are n and negative n, if this representation is n plus 1 dimensional, you remember. So they are 2 beta alpha divided by alpha alpha plus 2p, and 2 beta alpha 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 plus 2q, right? And these two integers are opposite to each other, n and negative n, right? Their sum is 0. Their sum is 0. What do you think their sum is? The sum is 4 beta alpha divided by alpha alpha plus 2 p plus 2. PQ depending on beta and alpha. I can write p beta alpha, q beta alpha. This is 0, which certainly means that alpha beta is equal to alpha alpha. Let me write minus alpha alpha times p plus q divided by 2. Okay? This rational, p and q are integers. This very much rational relation. This is not all. This is an important formula which I'm going to use immediately. But first let me write, and we know this from, I don't know, previous lecture, earlier, the following thing. Suppose that we have an arbitrary element C in H. I can write H. H and H. Very arbitrary. Then the following holds. This is equal to the sum over gamma are roots. I write here dimension g gamma times gamma of h squared. What about this formula? Accept it. Dimension g gamma is 1. Certainly, if gamma is 0, it is not very much 1, but then gamma of h is 0. Right? So this is actually the sum of the squares of this gamma of h. Very interesting. Not too much so far. But assume that we want to know H alpha, the same as alpha alpha. Right? Then I have this sum. Now I prefer to note this beta because I have a formula. Beta alpha squared. The value of beta on H alpha is the inner product of beta and alpha. Okay? You should stop me as soon as you don't understand. But for beta alpha, I have a formula. Is it still here? Yes, it's here. It is in the same board. I want to plug it. Beta P beta alpha. I mean, this depends on both roots. It is related to the root series. Who am I to teach you elementary algebra? Alpha alpha is equal to this. From this, we immediately derive a formula for alpha alpha. I cancel alpha alpha. And I write alpha alpha is the sum for over all roots beta p beta alpha plus q beta alpha over 2 squared and all this inverse. What about this? No comments. One important comment. Alpha is what? A complex number? No. It is a positive rational number. It is rational, and it is not negative because of the sum of the squares, but positive because alpha is not zero. So this is a positive rational number. Very interesting. But we had a formula for alpha beta. I have just erased it, but you remember. From this it follows that alpha beta is rational for every two roots alpha and beta. Because alpha beta is equal to alpha times some number which is definitely rational. Maybe negative, but any problems? Very elementary. I am going, my lecture today will be at the level of elementary school, which makes it maybe difficult, but still. We discussed this last time. I can repeat it. From this it follows. So all roots have a rational, number one, all roots have rational inner products. Take roots. They span the space H star. Take there your choice, rational or real linear combinations. It will be a rational or real subspace of the complex vector space H star, right? And now I can say that the space of rational linear combinations has, as a rational vector space, has the same dimension R, dimension of H. Why? This is because it is spanned by a root, now over rationals. Roots are linearly dependent, right? So some roots are, we can choose a basis in the root space. And then some other roots will be linear combinations of these basic roots. But the coefficients can be found in terms of inner products. There are formulas which are known. And this implies that actually, if a root is a linear combination of basic roots with complex coefficients, yes, but these complex coefficients are rational numbers. So the space of rational linear combinations or of real linear combinations of roots is respectively rational or real vector space, but with of the same dimension. Okay? Now I had formula, if you remember, for HH. And I want to say that if H is a root vector H alpha, or a rational linear combination of root vectors, then this beta of H is a rational number. And the sum of the squares of rational numbers, unlike the sum of the square of complex numbers, is positive. This implies the following thing, which makes the whole consideration purely geometric, that actually this real or rational, your choice, vector space has this property that the restriction of the killing form to this space is positive. Any square is positive. Okay? If not kindergarten algebra, then at least elementary geometry. At this moment we can say, we can speak First, by the way, simply I want to say something which corresponds to our actual level. My Lie algebra. I want to say that actually what we deduce, we can find, I will discuss it later, but now it is clear that we can find in our complex Lie algebra a Lie subalgebra, real Lie subalgebra, of which this complex Lie algebra is a complexification. And this Lie subalgebra has the Killing formula of this real algebra is biased definite. This immediately happens. We have these H alphas. We have E alpha and F alpha, you remember. And we can consider these very elements, but take their not complex, but real linear combinations. And it will be Lie algebra. And our algebra is complexification. And the Killing form, restricted to the Cartan subalgebra, is biased definite. So we have this strange thing. We don't need it now. I just wanted to mention it. But now we return to roots in H, but also I can consider the real space or rational. Real is better because I have a real space on this blackboard, two-dimensional real vector space, and I can draw pictures. My first thing, actually we discussed it last time, but last time I had to cheat. Now I don't need to cheat. Consider two roots, any two roots, your choice, alpha and beta. But now we consider them as element of a real vector space, spanned by roots. And I have this, alpha beta 2 divided by alpha alpha is an integer. This is also an integer. And their product, according to the elementary formulas in linear algebra, is 4 times cosine squared. 4 times cosine squared of alpha beta. Cosine, you know, is something which cannot be arbitrary. Its square is a number between 0 and 1. If we multiply this by 4, it will be a number between 0 and 4. 4, well, cosine can be 1, I believe. Cosine square is 1. If alpha and beta are proportional, the angle is 0, 180 degrees. If we drop this case, because we know all cases when alpha and beta are proportional, then this number is less than 4. Do you know many integers which are less than 4, positive integers? I personally know only 0, 1, 2, and 3. So the square of cosine is one of these numbers. Right? Which makes our choice, well, also 1. This is the case when alpha beta proportional. This makes our choice for the angle between alpha and beta very much limited. Is it 30 degrees, 45 degrees, 45, 60 degrees, 90 degrees, yes. And also 120, 135, and 150. Right? Very interesting. But I can say more. I can say more. This number, this integer between 0 and 3 is not just an integer, but a product of two integers. Right? So these two integers are plus minus 1 and 1, 1 and 2, 1 and 3, or minus 1, minus 1, you understand. You can change the sign for both, not for one. This gives you a lot about a lot of geometric information about the roots. Not only the angle between two roots should be one of these angles which I listed. The length, that is the ratio of these two numbers. This is the square of the ratio of the length. Is also 1, 2, 3, or 1/2 or 1/3. So actually, for roots now, geometrically, we don't have too many possibilities. Consider series of roots. So this is alpha. Say this is beta. And we add alpha to beta. What we have actually, we have a symmetric sequence of points in the plane, which is spanned by these two roots, right? Which look like this. What are the actual possibilities? This is a possibility in the case when this angle is 150 degrees. Then cosine is square root of 2 divided by 3 divided by 2. The square is 3/4, and the length of my series is 4. Looks like this. If this angle and the ratio of the length is square root of 3, you understand? Also visible from this picture. This is another possibility. It's 1 degrees. And one more possibility. The angle is 120. I want to say that this is if two roots alpha and beta are not orthogonal to each other. This case is also interesting, but we will consider it later. Then actually we have this configuration of roots. One of these three configurations. The first immediate thing which we can get from this, we can get a full description of possible system of roots in dimension of one also, but 2, 1 and 2. 1 is trivial, 2 is less trivial. So suppose that first R is 1. I even don't know what I need to say about this case. Then my space H starts when the dimension is line. And the only possibility for the three roots is this, right? Can you say now what is the inner square of alpha? Because it can be, you can find it now. Don't believe? There is a formula. It's not on the board anymore. You remember, the inner square of alpha is the sum over all roots of the squares of p plus q, p beta alpha plus q beta alpha divided by 2. This is squared, and the sum should be inverted. There are three roots, right? What are, I take alpha. So, if I take a root beta, one of these three, and alpha is this, then here, P and Q are negative 2 and 1 and 0. Okay? Here it is negative 1 and 1. Here it is 0 and 2. The sum of these three pairs P and Q. It is, I believe, in these two cases, this is 1. In this case, it is 0, so this is 1/2. 1 plus 1, which is 2. My word for that. When you take the inverse, it is 1/2. So actually, alpha is 1/2 in this case. There is a Lie algebra with this system of roots, and it is SL2. It is very much three-dimensional. The dimension of Lie algebra, if it exists for this geometry, the dimension of the Lie algebra is 1, because R is 1, plus the number of non-zero roots. 1 plus 2 is 3. Three-dimensional algebra. And this is precisely the three roots of SL2, alpha, negative alpha, and 0. This case is not very interesting. Now let us consider other cases of dimension 2. I will need this configuration, but still I erase them. Suppose that there are at least two roots, because suppose they're not orthogonal to each other. Then the angle between them, you know what it is. Suppose that the minimal angle between roots is 60 degrees. It could be 60, 45, or 30. Then there are two roots of the same length, with the angle of 220 degrees, right? One more root here. We know that in this case, the series of roots has this length. These three roots also have, if alpha is root, then negative alpha is root. And I can say that in this case, if the minimal angle between the roots is 60 degrees, there are no other roots. One more root will be at least one angle less than 60 degrees. So this is a possibility for four roots. 6 non-zero roots plus 1 zero root. And one important thing. The length, alpha. In this case, this is alpha. I must know by alpha. And at every point, I write P and Q. Here, negative 2, 0. Here, negative 1, 0. Here, 0, 1. Here, don't you see what I do? For every point, I just look how it is possible within the system to add alpha, or to subtract alpha from this root. And this is visible. So here again, I have 0, 1. I have, 0, 1. It's here and here. Now for these 6 pairs, I need to add them, well, to square the results, to divide them by 4, to add all the 6 numbers, and then to take inverse. It will be 4 times from this 4 plus 2 times 1 inverse, and this is 1/3. Any comments? So we have 6 roots in this case. I pretend that I do not know the Lie algebra. I simply look at the geometric possibility for roots. And my result is that it is possible. There are 6 non-zero roots, all of the same length. They form a regular hexagon, and all the squares, all the length, are 1 divided by square root of 3. All the squares in a square are ever is equal to 1/3. Any comments about this? Now, I am busy making system of roots, but I didn't say, I'm going to say it now, that there is a Lie algebra with these roots. There is a Lie algebra. It is SL3. It is a different story. We need to identify the algebra. SL3 has dimension 8. 9 minus 1. 3 squared minus 1. And we actually know Cartan subalgebra is two-dimensional. We know roots. We know everything about this. And we can make the computations. It will be 6. We will have 6 roots with this inner squares and lengths, as shown in this picture. The second possibility, if you don't have questions about this possibility, second possibility is that the minimal angle between roots is 45 degrees. Where are we now? In a class of elementary geometry, right? I will erase this simply to make some space. The angle is 135 degrees. The ratio of length is square root of 2. Okay? At any moment you can interrupt me with questions. We must have this. The length of this series should be this, which immediately gives you this system of roots. Eight non-zero roots. Nothing can be added to it again. These are roots, should be roots, but no more roots, because any root which is not on this picture, we will make an angle less than 45 degrees. There are 2 lengths, right? Ratio is square root of 2. We can compute both. Or we can compute one and then the smaller one and multiply the result by square root of 2. I write P and Q. Right? Same. Same. Okay? If it's really okay, then of the sums we have 6 times 2 and 1 time 0. 2 times 0. So if this is alpha, this for this alpha, I wrote this, then alpha is what? 6 times 1 if this is beta, this will be 1/3, because it is 2 times more. Questions about this? Also possible root system. I say possible, I can pretend that I don't know this is possible, but still it should be a Lie algebra of dimension 10. Do you know Lie algebra of dimension 10, which could have rank 2? Yes, no, it's 05. 05. 5 times 4 divided by 2 is 10, I think so. So this is 10-dimensional Lie algebra, O5. And again, it is not hard. It is still requires some work. There was an exercise. But if this work is done, then yes, the algebra O5 is, has rank 2. On in general has rank integral part of n over 2. Dimension is 10, and this is the system of roots for O5. But there's one more possibility, when the angle is 30 degrees. Very interesting. This picture wasn't on the board. So, no?
No, you're good.
Yes, then we have also this, and we have also this. Now, in this equation, I can arrange these things. Is it all? No. You see, this arises from this. Also, we can consider what? We can consider this series, which is produced by what? By these two. Also, the angle is 30 degrees. There should be one more vector here. Now I can even write, if this is alpha and this is beta plus alpha, beta plus 2 alpha, beta plus 3 alpha. So the step is beta plus 2 alpha, minus beta minus alpha, and then minus 2 beta minus 3 alpha. And a vector here which is symmetric to it, which is 2 beta plus 3 alpha. Negative beta should be somewhere here. I don't know, we can exercise our knowledge of geometry speaking of this system of vectors. Certainly no more, nothing else, because the angles are all 30 degrees. So we cannot insert anything else. Those of you who can count these many points understand that there are 12 non-zero roots and 1 zero root. Whatever you say about, well, I will not make the computation, just maybe you find it boring. I will not make the computation of the length. The inner square of alpha is 1/12. The inner square of beta is 1/4. It is 3 times more. A Lie algebra, if it exists, must have dimension 14. Right? 2 plus 12 is 14. Have I ever heard of a Lie algebra of dimension 14? Huh? You know, yes. You know, there are so-called classical Lie groups, Lie algebras, and 5 exceptional Lie algebras. And here we actually find the first example of an exceptional Lie algebra. The common notation is G2. The dimension is 14. There is a classification of simple Lie algebras. 4 series. One is SLN. One is 2. ON provides 2 series because they should be separated, even an odd n. Also SP, something which we can now discuss here. And you know, they all have their dimensions, root systems, and everything. Also 5 exceptional Lie algebras, which some of them are very important. G2 is the first of them. It has dimension 14. There are several more. F4, E6, E7, and E8. They all have dimensions. The dimension of E8 is the biggest of them is 248. Dimension of F4 is 52. Dimension of E6, I think, 78. And also some dimension of E7, maybe 126, but I'm not sure of that. Yes. Now, to finish all this story, you can have this impression, I wanted to create it, and if you have it, then it was my goal. That actually, with the geometric information of roots which we have, it is not difficult to classify them for every dimension. In dimension 3, very interesting geometric work. You can try to classify all system of roots in dimension 3. The easiest, the simplest of them, which belongs to SL4, is the following. Have you ever heard of, well, certainly you all know regular polyhedra. Yes, but there is, I think, a semi-regular polyhedra. Do you know what it is? Polyhedra, their faces are all regular polygons, but with different number of sides. The best of, well, the one which appears here, you can try to do this. Can you imagine a polyhedron which is made out of 8 equilateral triangles and 6 squares? Maybe I will bring a model next time. It actually, it has 12 vertices, and this is a root system for SL4. There are 2 more. One is very simple. You just need to, so you take vertices of this polyhedron. The same polyhedron, same vertices, plus centers of squares. This is something which belongs to 07. And one more. Also the same amount of vertices. Now let me, well, can you give me the opportunity to say something in 40 seconds? You know, there exists a way how to classify root systems. It is the following thing. You see, these pictures still are complicated. Take a chalk and then divide this plane into 2 parts. Then, very arbitrary, take this positive, this negative. Positive roots, negative roots. Simple, these are positive. Simple positive roots are positive roots which are not linear combinations, which are not sums of other positive roots. There are two simple positive roots on this picture, you see them. Everything is fully the same in any dimension. Everything is fully determined by simple positive roots and their inner squares. This system of simple positive roots, which is usually presented as a diagram which is called Dynkin diagram, I will show this next time. And then it is very easy to classify all the possibilities, not in terms of root systems, but rather in terms of systems of simple positive roots. And this is what we are going to do next time, and this is very simple. Next thing, it is true that if 2 simple Lie algebras have the same system of roots, then they are isomorphic. So what we do actually, we classify all simple Lie algebras. Thank you for your kind attention.